All right, it looks like it's working. Okay. This morning we have a request for some grade 9 stuff. And this person comes from Instagram, and she sent me a few pictures. So let's see what we can determine from these pictures. Ooh. Looks like angles. Angles of lines first, okay. Volumes of cubes, parallelograms, etc. Tables and charts. Looks like mean, median, and mode. So we'll just have to look up and go through some definitions. Yep. Averages, ranges, angles. Okay. First and foremost, she's got problems dealing with lines. Now, the question with this is, how do we make this easier to teach? You know, this is it's questionable. How do we make lines easier to teach? How do we, besides just going through a definition, I mean, how can we make it simpler? Well, let's think about it. First thing we know is that a line is 180 degrees, right? And that's what everybody's taught first. So any sum of lines, let's say there's one here, there's one here, there's one here, there's like one, and no, that's too ugly. Let's think of an easier way. Okay, a much nicer way. If there was this angle x, this angle y, and the angle z, well, we already know that x plus y plus z is 180, because we know by definition a line is 180 degrees, right? So what do we have in her questions that would be difficult with that? Well, what about, okay, using the axes? The whole direction is 360 degrees. So that means all the angles would add up. Well, and we use the axes, and all the axes are 90 degrees. 90 times 4, 360. So what can we do? What kind of problems? How can we make it easier on her? That's about it. It's really just understanding the definition and how much angles be split up. We'll have to do one as an Instagram post, I'm sure. Let's do... talking about angles, angle bisectors. Okay, so another thing that she's got in here for her review is these two lines are parallel. Let's call it line AB and line CD. And then she's got this other line through here. It's not accurate, obviously, but it shows that this angle is 72 degrees. And what it wants to know is work out the size of the angle marked X, and this would be X. Okay. Now, without spewing a bunch of definitions, we know that, oh, I forgot to mark the parallel lines. Got to do that because that's important. So, without spewing definitions, how would we tell her that the answer to X? Without being too confusing. Well, this line, it's hard to say without actually just going through definitions. I mean, it bisects these two parallel lines, and since they're parallel, a line bisecting it creates similar angles. Similar parallelograms. That's really all there is. What else do we say? We say since line AB and CD are parallel, then whatever this line is, we will call it EF. What is it? Is it bisects? I should probably look up the absolute definition of bisects. Maybe I'm using it wrong. These angle ones I don't use very often. What's not equal parts? The line EF how would we say it? What's the proper way to say it? In a simple way, simple manner. Honestly, I would say it cuts through. Oops, I forgot to write the line. Then the line EF cuts the parallel lines with equal angles. Which means, so we know that this is 72. This angle here is 180 minus 72. Oh, look. This would be the exact same. We could say the opposite angles between the two are the same. This is 180 minus 72. This is 180 minus 72. Which then gives us this to be 72 degrees. The funny thing about early math is it sometimes can be so simple it's hard to describe when you know the advances of it. Okay, these are angles. Sometimes she'll be given just simple things like what is this? 70 degrees. And what is x? And we just go through 180 minus 70 is 110. Easy. Done. So let's go into the next stuff. She's got surface area. Looks like these pictures are a bit difficult to read. And she's got a cube. Now, cubes are always interesting to draw. Because I am bad at drawing. Nice. Did it, guys. I did it. So this is a 5 by 5 by 5. I'm so glad they have it in centimeters. Now, is there a way we could start talking about volumes and just kind of talk about like three-dimensional objects? As in like using the axes. Oops. So I want to go through using the axes instead. Because we know, well, this is the x-axis, this is the y, and this is the z. Because technically a volume is just using two-dimensional space. So let's say it's 5 and 5. Here's a 5. And we'll say this is close to 5, maybe. Pretty close. Not bad, not bad. So this is a distance of 5 centimeters, and this is a distance of 5 centimeters. And this is just the surface area of a square, right? Okay. If we've got a square surface, the area, which would be defined as that shaded in space, would be 5 times 5. Now, how do we make that into a cube? So here's 5, and here's 5. Well, we have to go up a distance of 5 up here on the z-axis, right? And we could think about how would we because I would say we take slices and we'd add them all up. Let's say 1 centimeter sliced, but then that still have to multiply it. I'm just trying to think what would be a nice way to describe areas, volumes. Well, it's taking the height and having and taking the limit. But that's just too complicated. What would be an easy way to tell a kid? Boogie's doing math? When did Boogie do math? That's awesome. The way he finds the answer. That's awesome. I think he actually didn't understand the question at all. Because the looking at the it's hard to tell based on his camera, but it looks like the question is actually just asking to show the answers. So f of x is that function, and then shows what happens when you plug in 4, when you plug in 0, when -3, when you plug in 6 minus t, when you plug in 7 minus 4x. So technically each one of those has its own answer. He's not supposed to just pick an answer. Still waiting on this this girl to respond. I know, it does make it more funny. Maybe one time later we'll have to do like stupid things. Maybe you can help me figure out how do you tell young kids a simple way to do simple math without having just to bombard them with definitions. That's what's interesting, is to try and figure out how to teach people without just telling them explicitly, by getting them to figure it out. Like, I was thinking of doing a similar concept with like surface area. You know how you have like a line segment and it takes up this much space? And this is like 1 centimeter, 5 centimeters. The only thing is, by itself, that's just telling you what the surface area is, and then you can just apply it to a larger space. I think we'll just have to go through basic definitions to really tell her. There's not much else in this grade 9 math. Honestly. Like, how to determine the volume. You just multiply each sides. You don't think you're that smart? You're probably smarter than you think you are. Okay. I might as well do an Instagram post while we're waiting. So what should we do a question on? What kind of topic? Let's see. There's grade 9, grade 10, grade 11, grade 12. First year. You're a meathead? I don't know, man. Meatheads, they have brain function power too. Like, it takes a lot of brain power to know how to lift things. Especially with technique. Because you figure out your lever arm. How to use your muscles effectively. It's all in there. That's really all there is to this stuff. Like, I don't know how people teach grade 9 so easily. Or if they do at all. Elementary school must drive people nuts. Oh, you know what? I should use... I'm going to turn this background off. Give me a second here. Whew, paint bucket takes forever. Okay. Let's try and do a little bit of this parallelogram teaching thing. Okay. I'm going to copy this. wonder if this will work. Nice. Ha! Brilliant. Figured out something that'll cheat. So, we want to take this and we are going to flip it. Would that be the best way to do it? No. No, that's fine. Because then we can use that idea. Say, oh look, we cut that off. Now we've got this onto here. Now we've got a square. Ah! I think that'll help teach. Okay, yeah, that's enough of that. Okay, let's do some actual stuff while we wait. Grade 9 is weirdly tedious. But that's okay. Foundations and pre-calc. Lines. Radicals in simplest form. Okay. Let's say screw it and do calc. I know what you mean. Fitting a lot of content into one post is difficult, but cramming for a test is even more. Honestly, with some of the requests, so like I did one earlier where it was on matrices, and I realized that I had to split it up into multiple pages just to get it across, but doing up to like 6 of those little notes, I think it helps. I really don't know any other way to get it across. Simple notes is the quickest stuff. Yeah, 1 of 3, etc., all that stuff. So average value of a function would be relative. Let's do some calculus with areas. That's a good thing to do while we wait. Okay, so the area between curves. So let's say we've got a I'm gonna change the colors. Good. Okay. Let's say we've got a curve like so. And we've got another curve like so. No, it didn't change. So this will be, let's say our x equals, no, I'll do regular functions first. Poor brains, you're getting all flustered today. You must be tired still. Let's do regular functions first. There. So we want the area between these two curves. Okay. So this one will be y equals f of x, and this will be y equals some function g of x. So the area between these two curves would be what? The top one minus the bottom one. So when you think of areas, now the integral does give the area beneath the curve, right? So we can think of, well, fundamentally it's like taking small slices until you get an infinite amount of them, and then you have the full area. So this area will be the integral from, this is a and this is b, and we've got, yep, cool, I even wrote it the same as the textbook, a to b f of x minus g of x. Now, some of them, now do they incorporate the absolute value? For multiple curves, yes. Dx. Okay. What does this mean for functions that cross? Well, it just means that we have to swap them around, change their signs if they become crisscrossy. So an example. Let's say we've got some function like this and another function like this. So this one will be our f of x and this will be our g of x. And this is some point A, this is some point B, some point C, and we'll call this some point D. Now, over here, in this region A, and this is region B, and this is region C, in region A, f of x is greater than g of x, so that's fine. In region B, and region B, we've got g of x, if you follow, is above. And And then we've got in region C, f of x is back above, so which then just means we have to split up this integral between those pieces and change the signs because we want the distance to be positive. So we'd have the integral from a to b of f of x minus g of x. Then we'd have plus the integral from b to c of g of x minus f of x dx. And then we'd have plus c to d of f of x minus g of x. And that would give us our full area of these region A, B, and C. Okay. Do we have any problems to do? Yeah, okay, cool. Let's do some example ones. Find the area of the region bounded above by y equals e to the x and bounded below, so and y equals x and bounded by the sides x equals 0 and x equals 1. Okay. First we'll take a look. If you know what the graphs look like, it makes it a little easier to understand because you'd want to find points where it would change in size. So y equals x, if I can graph it more accurately than that. Ha! Better. It's pretty close. It looks like that. It's just a straight line. So y equals x. And then, well, y equals e to the x would look something like this. Where would they intersect? E to the x would be, when x is 0, it's 1. Somewhere else. You had a weird cat face? Upper and lower bounds. You got scared. In what context? So I've got another person asking, make a post about upper and lower bounds. Okay. I'm gonna cheat slightly. Okay. They have no intersection. I'm going to try my best to graph this. Yeah, that's pretty close. There. Honestly, it's just all the stuff I've ever known. I wouldn't say I'm smart though. I'd say I'd just be more versed in one language than another. Because mathematics is a language. I can speak English, but I can't speak French. I can't speak Mandarin. I can't speak Spanish, any of those. But I speak a little bit of math. So that's the difference, right? It's not that I'm smart, it's just I've learned a different language. Okay. Other bound, so this would be like a left bound, would be at x equals 0, which is right on the axis. And then x equals 1, we're going to say it's somewhere over here, just to make it a little bit more visual. So the region that we're going for is in here, which would be what? Well, if we're integrating with respect to x, we'd go from what, 0 to 1? And then we would have e to the x minus x dx. Because e to the x is the upper bound function and y equals x is the lower bound function. Is there any other more interesting ones? Nah, whatever. So then area, we would just integrate this. And the integral of e to the x is just e to the x. And minus x would be minus x squared over 2. And we'd evaluate between 0 and 1. So e to the 1 minus, well, 1 squared over 2 is 1/2 minus e to the 0 minus, well, 0 squared over 2. So this would be the area is equal e minus 1/2. E to the 0 is just 1, so minus 1. So our area is e minus, what, 3 over 2? And if we write it as a decimal, 3 over 2 is just 1 and 1/2, so 1.5. And so what's e? 2 point something? Another one. And another one. I've got somebody requesting bounds. What? Upper and lower bounds. I wonder what context he's referring to. Let's see if I can Google something about his class. Well, that was useless. No good. Whatever, back. Maybe he'll respond with some information for me. Okay, next one. Area enclosed by two different parabolas. So we've got y equals x squared and y equals 2x minus x squared. I wish Instagram had the capability of just sending you a message on desktop instead of always having to check your phone. Okay, let's graph these. The first one, y equals x squared, is just the standard one, so that's pretty easy. Let's put the other one in vertex graphing form. We got minus x squared plus 2x. I'm going to take out a minus sign so that I get x squared minus 2x. And I want to get it into the form, so it's some value a times x minus p, let's say, squared plus q. I want it to look like this, with some values in for a, p, and q. So what I'll do is I'll complete this square. So I'll take half of the negative 2 and square it. So, well, what would that be? Plus 1 minus 1, right? So we'd have x squared minus 2x plus 1 minus 1, which would give us y equals, well, this is the same as x minus 1 squared. You multiply it out, so you'd FOIL minus 1 minus 1. X times x is x squared minus x minus x, and minus 1 times minus 1 is plus 1, so plus 1. See, we'd get the same. So this would be minus, and I'm going to put it in two brackets here, x minus 1 squared. We still have a minus 1. We're going to distribute the negative now. So y equals negative of x minus 1 squared plus 1. Now it should be easy for us to graph. Okay. I'm going to put this right here. Here's our y, here's our x. Now, you can look for their intercepts a couple ways. One by graphing, if you graph accurately, or you can set them equal to each other and find out where that is. So let's try that. Where's the intercepts? So the intercepts is where their y values correspond. They're the same. So then that means the y's would be equal. So you could say x squared is equal to 2x minus x squared. So let's take everything over to the one side. Let's take the minus x squared over, so we'd have 2x squared. And then we'd have minus 2x. Okay, this would be equal to 0. If we take out a 2x, then we'd have these values. Which means we would have, well, the 2 doesn't matter. If we divide that out, we'd just have x times x minus 1 equals 0. So what capabilities, or what values of x give us 0? Well, that's x equals to 0, and well, when x is equal to 1. Okay, so we know an intercept is at 0 and at x equals to 1. Let's try and, well, I'm going to graph the first one, hopefully not too ugly like. Nope, that was pretty bad. A little better. Okay. Now, -1 plus 1. Vertex. Okay. We've got a -1 shift to the right. We go about here. And +1 would be here. This would be our vertex. It would go negative with a standard pace. This is our region, right in here. A little small, probably could make it a bit bigger. But this is our y equals x squared, and this is our y equals 2x minus x squared. Okay, now we found our regions, we found our points, now we just need to find our area. So what is our area? Area is the integral. Well, this is between 0 and 1. And the upper bound function is the 2x minus x squared. So we'd have 2x minus x squared. And then we're going to subtract the lower bound function, which would be minus x squared dx. Nothing yet. Okay, cool. What will that give us? Well, then we've got area equals integral from 0 to 1, 2x minus x squared is just minus 2x squared dx. Then, well, we could take the 2 out. That might make it a little simpler for us. 2, 0 to 1 of x minus x squared dx. Now let's integrate. Integral of x is what, x squared over 2. And the integral of x squared is, well, that's x cubed over 3. And don't forget, we are still multiplied on by a 2, and we are evaluated from 0 to 1. Okay. Let's evaluate. Well, we'd plug in a 1 first, so we'd have 2 times 1/2 minus 1/3. And then we'd have minus of 2. We still got to keep our 2 in front. And, well, it's 0 minus 0. Oops, not over 0. 3. Which means this part here is all 0. So we're left with just 2 times 1/2 minus 1/3. Which, if we want, we could just say is 1 minus 2 over 3. 2 over 2 is just 1, right? And which equals 1/3. That is our area between those two curves. Now eventually we'll start going into like a volume, rotating around an axis or around a line or anything like that. So we'll get funky shapes. Which will be interesting. Not yet. Okay. What about different kinds of functions that work better in y rather than x? Well, let's go back down a bit more. So before we were doing well, let's talk about this. So the integral is basically the area under the curve. If that's our curve, and this is our region points A and B, the integral gives us this area, right? Okay. What does that really mean? We are basically taking our function. Now this is a function with regards to x. We are taking little bits and we are adding up all these areas. And kind of want them to be the same size, but I'm not the greatest at cheating and drawing. So you take all of these all the way along, and you would say you would take the sum of the areas. So this would be a plus h in these areas, and you take the value of the function at that area. And you'd sum them all up because, look, it's just a rectangle. And a rectangle has this height and this base. The area of the rectangle is just base times height, right? Well, what an integral does is it takes all of them to the point where the base becomes infinitely small. So it gets smaller and smaller and smaller and smaller and smaller until it's essentially not there. And that would give us the exact area of the whole of under the curve. So we were dealing with x, and it was top down. So now if we take it from the y, let's say we have our function, whatever it is, that looking like this. If we integrate with respect to y, it's essentially like rotating 90 degrees, right? So then we would say that it's these areas instead. and all the way down. So if we have an area between two y value functions, it would be the rightmost function minus the leftmost function. So, see if this person got back to me. Nope. Okay. We will do a question dealing with two different types. So, what we've got, region bounded by y equals x minus 1 and y squared equals 2x plus 6. We need to find these two functions. Well, y equals x minus 1 is really x equals to y plus 1. And this one, y squared equals the 2x plus 6, is really, well, you take away a 6 divided by 2, y squared over 2 minus 3 equals x. Okay, now we got to graph those functions. Just so we can kind of gauge where they are. So x equals y plus 1 would be still a horizontal line, or we could say y equals x minus 1. Or not horizontal. Just a regular line. And it would be 45 degrees. Still, since there's no change in slope, I'm going to try. Not bad. Okay. We'll say that's y equals x minus 1. Or x equals y plus 1. Now the other one. This would be minus 3 dropped on the x-axis. So if we think in terms of rotating, if we looked at it the other way, minus 3 in the drop would be somewhere over here. And then y squared over 2 would be moving positive in the x direction, and it would have a reduced slope. I did not draw that dot good enough. Should draw it over here. Yeah, that would look a little better. Then we should have a parabola of this nature. Okay. Parabola like this. Where do they intersect? Well, we've got x equals y plus 1. Oh, I've got a phone call. I will be 1 moment. Phone calls. I never liked those things. But apparently I don't have to cut down trees today. That'll be tomorrow. Okay, back to doing this area. We need these intersection points now. So we would do that where x's would be equal. So we'd have y plus 1 is equal to, y squared over 2 minus 3. Right? Okay, so let's get this solution figured out. So let's multiply everything by 2 after we bring the 1 over. So we'd have y equals y squared over 2 minus 1 to both sides would be minus 4. We'd have 0, and now we'll bring the y over. We've got y squared over 2 minus y minus 4. We'll multiply by 2 across everything to get the y squared simplified. So we'd have 0 equals y squared minus 2y minus 8. So multiply by 2. Then 2. Well, we gotta factor this. What two values, when added together, give you minus 2, but multiplied together give you minus 8? Well, I'm going to write this in first. Multiply to give us minus 8, but add to give us minus 2. Well, 4 and 2 are factors. If one of them was positive and one of them was negative, they'd multiply to negative 8. So we'd have, well, looks like the 2 would be positive because minus 4 would be a better value. If we go minus 4 and then add 2, we'd get negative 2. Which means these two values would imply that y is equal to 4 and y is equal to negative 2. Okay, which means when y is 4, that's up here, what is the x value? The x value will be, well, 4 equals x minus 1, add 1, x equals 5. So 5, 4. What about this value? This is y equals negative 2. So we'll put in negative 2 for y. Negative 2 plus 1 would be just negative 1. Right? And I'm going to write this a little clearer. This point here, negative 1 for the x, comma, negative 2 for the y. Okay. We want the area between these two curves. So this region, we're going to do it with y values this time. If we did it with x values, it might be a little bit complicated because this over here and this point here and this point here, it splits it up awkwardly. Plus, if we got below the curve, then we'd have to take multiple types. So let's do it with y values. So this is y equals x minus 1, and this one here is x equals y squared over 2 minus 3. Let's take our integral. We've got our integral from negative 2 to 4. This will be our area now. So we've got our lower bound region on the y to our upper bound region. We've got to take the rightmost function minus the leftmost function. So the rightmost function is this one, x equals y plus 1. So we've got y plus 1. And then we're going to subtract our leftmost function, which is y squared over 2 minus 3. And this we will integrate with respect to y. Okay, so let's just do some integrals. So the area equals, let's simplify first. Minus 2 to 4, we've got y plus 1 minus y squared over 2 plus 3 dy. 1 plus 3 is 4. So we've got the integral from minus 2 to 4 of y minus y squared over 2 plus 4 dy. Then let's just integrate. So the area will be equal to the integral of y would be y squared over 2, and y squared over 2, the integral of that, well, it's the reverse power rule, right? So this would be a minus y cubed over, well, 3 normally times 2, because the 2 is still on the bottom, and then plus 4y. We still have to evaluate from negative 2 to 4. So let's plug in some values. 4, y squared over 2. So we'd have 4 squared over 2 minus 4 cubed over 6. I'm going to leave it as, yeah, 3 times 2. Let's leave it as 3 times 2. Because then we can possibly get an easier reduction. Plus 4y, 4 times 4. Now we've got a minus. Minus 2 squared. So that's just 2 squared. 4 over 2 minus a minus 2 cubed over 6. And then plus 4 times minus 2. Keep needing to move over here. Okay. We've got, well, 4 squared, that's 16. 16 over 2 is 8. 4 cubed, so 16 times 4 again would be what? Well, what's 15 times 4? 15 times 4 is 60. 64. And 64 over 6. Let's reduce it. 64 divided by 2 is 32. So we've got 32 over 3 plus 16. 4 times 4. We've got minus 2. 4 over 2 is 2. Minus 2 cubed would be minus 8. But we got a minus, so now we're plus 8. 8 over 6. This is a plus 8 over 6. Now there's a minus in front, so we're back to a minus. Minus 8 over 6. This here, we've got a minus 8, now a plus 8. So let's keep going. 8 over 6 is 4 over 3 when you reduce. Because 6 is 2 times 3, 8 is 2 times 4. Okay, we've got a whole bunch of these that we can add and subtract. 8 plus 8 is 16. 16 and 16 is 32. 32 minus 2 is 30. We've got 32 over 3 minus 4 over 3, which would be what? 28 over 3? Oh, wait, no. You gotta subtract them. 32 minus 4 would be what? Why do I feel like I've got some wrong answers in here? Minus 8. No, that's good. Oh. Okay. Double check. No, let's keep going. 8, 24. 24 minus 2 is 22. We got 30, good. Minus 32 minus 4 is minus 36. Minus 36 over 3. Well, that's like 12, isn't it? So we've got 30 minus 12, which gives us 18, which is our answer. Haha. You never second guess yourself. Well, except for when you are wrong. Okay, this person wants upper and lower bounds. I'm going to be right back. When I come back, we're going to figure out a post for upper and lower bounds. Okay. A post for upper and lower bounds. Well, what is the definition of an upper bound? A higher... Let's think about a good way to represent upper bound. Let's see. We want to... How to represent... Upper and lower bounds. Well, an upper bound would be like its upper limit, upper capability, right? Let's think of different ways that upper bounds and lower bounds can be represented. So, it could be like a limit. So, let's see, an example of you can only buy so many 5-cent candies. Or let's see, a maximum or a minimum. What other words can we use to represent bounds? Well, graphically, like we were doing earlier, there's a couple of different ways. There could be let's say, let's do this line. Let's see. Oops. It doesn't look very good. Okay, so it would be this function, let's call it f of x. It would be an upper bound. And this one right here, this would just be some y of value. What's another way we could say it? Let's say we've got some absolute value functions. And this line right here. So if we were dealing with this area, we could do this line here is an upper bound. This line here could be a upper. It could be considered an upper bound if we were dealing with the y variable. So I'll call it the rightmost bound. But it could also be considered a lower bound, because if we were going left to right, it would be the rightmost, but it would also be an upper bound. If we're going vertically, it would be the lower bound in this case. It can be used for inequalities. So let's say a question about economics. your factory can only run if you make a certain amount of money, right? So you'd have a lower bound of income. If you go below that, well, then your company's losing money and you're not being profitable. You're going to lose your factory. Let's say an upper bound. Computer chips. Computer chips can only run in certain temperatures. They would have an upper bound and a lower bound. Because at the upper bound they'd fry, at the lower bound they would, they'd freeze out, whatever it is. Or water. Water. It only stays water between two temperatures. If it drops below a certain temperature, it freezes, and if it rises above a certain temperature, it vaporizes, becomes a gas. Now, there's variability to it, but that would be the case. So, like, we could talk water. Functions have upper and lower bounds if you are going between them, doing the area. What else? What else can we put? Functions, upper bounds, lower, upper line. Would be the maximum. So, like, in this graph, it would be like the area between. I'm thinking too far ahead. And it would be, so y has to be less than or equal to a, and y has to be greater than or equal to the absolute value of x. That would be this function here. I'll think about it. I'll make a post. I'm gonna stop for lunch, and I will talk to you guys later.